Okay, for this problem, I'm considering the system to be the bullet and the block, and the surroundings everything else. So here's a diagram of what's going on before the collision. So the bullet's traveling at that velocity. Here's all the different quantities. And for the final, it's worth mentioning that when the bullet embeds itself within the block, the way I consider that, the way I'm considering it for this problem, is that these two objects merge together and create one object, where their mass, I put here, is just the mass of the bullet and the mass of the block. And I wrote that here. And also, with that in mind, the final velocity of the bullet is going to equal the final velocity of the block. Very much worth noting, I would think. Okay. So part A asks about the speed of the block after the bullet embeds itself. And also, before I begin, I don't have any vectorized notation because we're only dealing with the x-axis because the bullet's traveling horizontally. So all of these are implied to be in the x directions. So we know, because our system was appropriately chosen as the bullet and the block, we chose that system so that we can use this equation right here, because the total momentum of the system is not going to change before or after the collision. So we can derive this formula here, or we can use it. And the total is adding up the momentum of the bullet and the momentum of the block. So here's the sum of the initial momentums, and here's the sum of the finals. This quantity right here, the initial momentum of the block, goes to 0 because the block's stationary initially. And we know by the momentum principle that the momentum equals the mass times the velocity, and that's applied for the rest of these parts over here. And because the final velocity of the block and the bullet are the same, these two values right here are the same, that and this. So I called that V sub f, and algebraically factored it out, and this is the value we're solving for. So divide by m1, m2, we reach this form here, plug in all the values, and I got that as the velocity. That's the final velocity of either the block or the bullet, in this case of that object merged together. Okay, I merged parts B and C together because they're pretty much the same thing. Calculate the kinetic energy before and after the collisions. Okay, initially we're dealing with I would regard that as the total kinetic energy, even though I didn't write it. So the total would be the sum of the initial kinetic energies, but again, because the block is initially at rest, that initial kinetic energy goes to 0. So we're just left with the kinetic energy of the bullet, where kinetic energy for very low speeds relative to the speed of light is defined here. And plug in the values, and I got this value here in joules. Dealing with kinetic energy, we like our answer in joules. The final, because I regarded the final outcome that when the bullet embedded itself within the block, that final object is just going to have one kinetic energy. Instead of thinking about the two kinetic energies, I just put it all as one. And it wouldn't be too hard to derive how to get to this form right here. But because we're dealing with the final kinetic energy of that one object, here's the mass of that that new object. Here's the velocity. And the velocity is that value we found in the last problem. Plug everything in, and here's our answer. And just because these two answers right here don't equal, we can conclude that this is an inelastic collision. Okay, the final part, I'll try to hurry up. Calculate the rise in thermal energy. Alright, so we know that the displacement of thermal energy, the total, is equal to the work within the system, which I didn't write system, but it's implied, plus Q. And Q goes to 0 primarily because of the system that I chose. And also because the collision happens in such a short duration of time that the heat transfer is negligible in this case. So with that being said, and also there's no significant objects in the surrounding. So with that being said, that's equal to the work, and we can define this displacement in thermal energy to be the loss in kinetic energy. But because we're dealing with a rise in thermal energy, naturally our answer needs to be positive. So that loss in kinetic energy I rewrote as this to intentionally get a positive answer. So here's those two kinetic energy values from the last problem. Plug them in. Got this value. And that's it.